Hello again. Today we are going to talk about one of the most fundamental laws in circuits, Kirchhoff's current law. I'm Fatima from the EC department of the University of Utah. In nature, KCL or Kirchhoff current law is pretty similar to law of flow. But what is exactly law of flow in nature? So as all of you know, in nature, when you have a confluence or a junction where rivers meet, always water flow in is equal to water flow out. Or for example, in this picture, I1 plus I2 is equal to I3. Well, so I have a curious friend. Her name is Mary, and she always wants to experiment all the theories to make sure they are really true. So Mary went and put the flow meters at confluence, and still she discovered measured flow in is equal to measured flow out. Or again, in this picture, I1 plus I2 was equal to I3. Due to her curiosity, Mary wanted to know what happens if she flipped the direction of measurements for one of the currents. Does the law of flow still hold true when the direction of measurements is opposite? So Mary flipped the direction of measurement for I3 such that minus I3 is equal to I prime 3 in the picture. What Mary discovered was that the summation of all the currents is 0, and always the measured flow in is equal to the measured flow out, despite the direction of measurements. And that is a good news. Means you don't have to worry about the direction of current measurements in your circuit, because KCL is very similar to the law of flow in nature. Now, let's show this with a practical example on a circuit board. This is a schematic of board we made ready for you. We have 3 currents in here, I1 going in and I2 and I3 coming out. We made the board that is exactly close to the schematic here. Okay, so now as you see in the schematic, we want to measure I1 in this branch and I2 and I3 in the other 2 branches, and see if really I1 entering this node is equal to the summation of I2 and I3 in here. So we show these I1, I2 and I3 with these yellow wires. I need to remove these yellow wires each time I am measuring a current to replace it with the ammeter, because the current has to flow through the ammeter in order to measure current. So now let's start with I1. If we actually remove these, we put the I1 is 2.75. Okay, so now let's measure I2. Okay, I2 is almost 1.1. Now let's do I3. Perfect, 1.65 almost plus 1.1 is equal to 2.75. And that validates our KCL rule. So as we mentioned before, the direction of measurements does not matter, and always the measured flow in is equal to the measured flow out. Let's also prove this in the practical example that we just showed you. By reversing the direction of measurements for I1, the ammeter leads are also flipped. As a result, we measure I1 to be minus 2.75 milliamps, and measured I2 and I3 of course stay the same as before. As you see in the schematic, all the currents are pointing outwards, and there is no current pointing inwards. Therefore, we expect the summation of all the measured currents to be equal to 0, and that is exactly what we get. So we can conclude the measured flow in is always equal to the measured flow out, no matter what direction of measurements you use, and that is the law of KCL. Thank you.